and we talk about subclasses of non-symmetric strings.
Okay, here the okay, so this is my title, and now you will see in the next slide that I will start to explore some difficulties that string theory faces when you try to go toward realistic, more realistic situations where supersymmetry is broken. I will address the conceptual point. Now this is probably known to everyone. It's a diagram that links together the 5-dimensional superstrings, but it's also a diagram which dramatically shows the limitations of our understanding of the whole story. Because if the upper corner didn't exist, we could be all satisfied. We would have a unique theory in 10 dimensions. But it turns out this theory is also linked to a theory in 11 dimensions which has nothing to do with strings. So which means that there is something that is missing in our understanding. And the key ingredient in this diagram is supersymmetry. Supersymmetry has a very important effect. It stabilizes vacuum. When the vacuum is supersymmetric, you need not worry about it, and you will see more details about this big help that it gives you. So the first question you can ask, given that supersymmetry is something that you don't see in the ordinary world, if we try to fit in supersymmetry in this picture, what happens? But first of all, what happens is that there are many more possibilities. There are many more options already in 10 dimensions. They are all linked to the 11-dimensional case. So that problem continues to be there. And another problem intervenes, namely that if you break supersymmetry, typically tachyonic modes appear. Now, if there are tachyons, it doesn't mean that the theory is necessarily nonsensical. It could be that we are expanding the wrong vacuum. In the standard model, if you expand it with respect to the wrong vacuum, you find a tachyon. However, in string theory, we lack the technology to move to the right vacuum. It has been developed to a limited extent, following Sen and others, for the open bosonic string, but already for the closed bosonic string, we don't know how to do it. The tachyon is there, we don't know how to live with that. So it turns out that there are 3 theories in 10 dimensions which don't have tachyons. And so we might start to explore what happens referring to those 3 theories, which I will illustrate in the following slides. And these are the 3 theories. There is an heterotic variant, a variant of the heterotic E8 cross E8 theory, this one. And there are 2 orientatives. So let me try to give you some brief hints. There is some technicality, but I will skip it most of the time. I just want to give you the message that these constructions are not arbitrary, rather they are highly constrained. They are highly constrained by the 2-dimensional structure that underlies string theory, and in particular, the vacuum energy is strongly built out of a couple of main ingredients. The first one is the so-called GSO projection, which is essentially telling you that you must respect spin statistics when constructing these modes. And the second is modular invariance, the fact that the one-loop partition function has to be invariant under the arbitrary choice of the time direction on a torus. If you do this thing, you can get this so-called E8 cross E8 heterotic string, and the partition functions have a dual interpretation. They describe the spectrum, and at the same time, they describe the back reaction of string theory in space-time. Now, there is an old formula of Jacobi that he called the equatio identica sasit abstrusa, that in this language tells you that numerically V8 is equal to S8. In other words, the back reaction of a supersymmetric string on space-time is 0. So you are happy you put the string vibrate in space-time, it doesn't back react, space-time remains as it is. This will fail as soon as we break supersymmetry. And now, how do you break supersymmetry? There is a crucial ingredient, like in quantum field theory, continuous symmetries are very important. In string theory, what it turns out that discrete symmetries play a leading role. And there is a procedure called the orbital projection, by which you take this theory, project out some states, and then try to reinstate modular invariance. If you do it, you get a unique answer. And here is the new spectrum. I described the master spectrum here below for you. When you see 08, you start to shiver because it means that you have tachyons, but closed strings have something called the level matching condition, so this tachyon is ineffective. Short is an off-shell state. In fact, off-shell states do run in loops. We don't know how to construct scattering amplitudes for off-shell states because it's complicated. Instead of having local operators, you would have large tubes. So now, this is the first theory. The second theory is more complicated than that because it has an open sector. But to make the story short, it starts from one of these tachyonic 10-dimensional theories and throws away the tachyon. The price from throwing away the tachyon is to have an open sector, which is chiral, like the closed spectrum. And then you get a theory which has an U32 gauge group. In fact, it is SU32 gauge group. Now, this theory contains amplitudes which have boundaries, like the annulus, and as a result, the perturbation theory is more complicated. It doesn't contain only integer loops, if you want, or even Euler characters, also odd Euler characters. Then there is a third theory, which is even more puzzling, and this theory is obtained by a minor modification of the SO32 superstring, just changing this sign, which has a reflection coefficient that can be adjusted. If you do that, then you get an open sector which violates supersymmetry, and a closed sector which is still supersymmetric. If you look at things more closely, you see that the open sector, however, contains a Gauss-Eno. So supersymmetry is not violated at random, it is broken spontaneously, albeit in a non-linear phase. Now, this is something that it's been bothering me since I stumbled into the story. All the cases of non-linearly realized symmetries I know of are limiting cases of linearly realized ones. If you know other alternatives, I would be happy to know. But, so it is striking that in 10 dimensions there is one theory which, where supersymmetry is not linearly realized, and it has all the other consistency conditions of the rest. I would say it is as puzzling as the link to 11 dimensions. Nonetheless, this theory exists. I added the story because we always discuss with Gia, because Gia went to build a theory of this type from a field theory viewpoint. Theories where supersymmetry is broken on branes, but exact in the bulk. This is what happens here. And from the two-dimensional viewpoint, I came to this story from a different path, which is essentially finding apparently inconsistent equations that become consistent once you allow for the breakdown of supersymmetry. Now, what do you do with these theories? You are a bit in trouble because string theory, as we know it today, and it's very incomplete, it's a double series expansion. You are expanding in curvatures in terms of the string scale, and you are expanding in loops. So a double series expansion, the only thing you can do effectively, you start with the Lorentz effective field theory. The Lorentz effective field theory is the starting point of a double expansion. So you are ignoring, at least they are very complicated to deal with, arc squared, arc cube, and so on terms. Why do I say that? Because you can add them, but supersymmetry constrains them. And remember, this theory starts as supersymmetric theories with some deviations. So you have to complete the arc squared and arc cube terms, and this is very complicated. So we start with this theory, and a priori we have no chance of success, or limited one. But these theories have a novelty, so they remember that supersymmetry is broken. How do they remember that supersymmetry is broken? There is an addition here, which I call generically tactile potential, and it depends on whether the theory contains or does not contain open strings. This changes this exponent, which has to do precisely with the loop expansion. String theory is little predictive, but is very predictive insofar as that exponent is concerned. If open strings are present in the model, the exponent starts like this in the string frame. Notice that Einstein gravity is accompanied by e to the minus 2 phi. This is called the string frame. If I go by this scaling, this coefficient becomes 1, and this becomes e to the 3/2 phi. What does this coefficient do? There is a striking little factor that keeps on attracting my attention. The first setting in which you can study this story is cosmological solutions. As you know, this is the standard equation for the scalar field in cosmology. And here is the same equation reformulated with 2 steps. One is just a convenience rescaling of the field. And the other one, more importantly, is a special choice of time, which is allowed by the fact that we are dealing with an exponential potential. With generic potential, you couldn't do it. With an exponential potential, you can use, if you want, the potential to define time. If you do that, then you get an equation which is a bit simpler than the previous one. And actually, it is very simple if you ignore the red terms. But even if you keep the red terms, already this equation tells you something interesting, that the driving force in this way of doing things is determined by the logarithm of the potential. So for instance, the logarithmic derivative of the potential for a power-like interaction goes to 0 when the field is large, which immediately is consistent with the fact that when you have quadratic potential, you inflate far from the origin and you start to oscillate nearby. The exponential potential is special because the logarithmic derivative is everywhere the same. But it still depends on this parameter gamma, and the question is how does it behave when gamma changes? Now, let me skip this analogy, and let me tell you that people studied this exponential potential starting from the 1980s. The famous result of the time is the so-called Kimada-Rays attractor. People talked about power-like inflation. Now what happens is that with this rescaling that I did, power-like inflation occurs for gamma less than 1. In fact, in 4 dimensions, gamma less than 1 was square root of 3. But you see that effectively, in this way of representing matters, in the inflation, the scalar attains a limiting speed. And this limiting speed becomes singular when gamma goes to 1. Now what happens with gamma when gamma goes to 1? The behavior changes completely. For gamma less than 1, the scalar can emerge from the initial singularity, climbing up the potential, or descending it. In the limiting case that the potential is not there, if you want, it can emerge from the left or from the right. When gamma becomes 1, the behavior changes abruptly. The descending scalar has no room anymore, and the scalar can only climb up the potential. You can say, okay, but in string theory it does make a big difference because the exponential of the scalar is the coupling constant, which means that this kind of dynamics is confined naturally to weak coupling in string theory. And this is the kind of story for the climbing scalar. If you want, this is the argument that shows to you analytically that the descending solution disappears when gamma equals 1. So if you want, we started with 2 problems, strong coupling and high curvatures, and in some sense the theory solved 1. The reason why it solved 1 because gamma equal 1, amusingly enough, corresponds precisely to the orientical potential, the one that I showed you for two of those 3 models. For the third one, the potential is even steeper, so it's well within the climbing region. The question, can you do something with a situation like this? Now, the obvious thing that comes to your mind is that if the scalar climbs up, then at some point it will lose energy, and then in the descent it will start inflation. So it could be a situation in which the scalar accumulates some energy, which is then released in the initial phase. What can you buy with something like this? Well, first of all, this kind of situation can be combined with potentials of different types. For instance, in this case, I'm combining it with the Starobinsky potential. This is the Starobinsky potential, and this is the wall that the scalar cannot overcome. So if you want, the initial condition is fixed. You cannot have any choice. The scalar has to climb up if you, of course, are daring enough to try to go back to the initial singularity, where, however, you're not protected by higher derivatives, so you should keep in mind that there is a proviso in this story. But if you do, then the scalar can only go up here, bounce back, follow the usual Starobinsky story and then oscillate and reheat at the end. What do you gain by this kind of situation? The situation, what you gain is that you can perhaps find the post-diction for the low power that is present in the first multiple of the CND. And this is essentially the power spectrum that you find for this kind of phenomenon. The little peak corresponds precisely to the scalar that inverts its motion. So it's temporarily in slow roll and then it accelerates again. The behavior is not universal because it depends, if you want, on how hard the scalar is hitting the wall. But what is universal is a cut of the power spectrum. The cut can be parameterized with this formula, which is actually following from it's an exact solution of the mechanical cycle equation, which obtains if you shift out the potential a little bit. Now, the parameter delta and this formula, which is vaguely reminiscent of a massive propagator with respect to a massless one for quantum field theorists, this formula here can be subjected to a test, and I was fortunate to collaborate with some members of the Planck collaboration to set to subject delta to a test. Now, one of the things you learn talking to these people is that the more parameters you put, the more baroque it becomes and you don't get anything. Delta is a single parameter. What happens if you try to fit the data with delta? What happens is that the situation improves if you stay away from the galactic plane. But the galactic plane, those of you who know these facts, is reconstructed because the galactic plane is dirty because of light coming from sources present in the galaxy. And if you go outside the galactic plane, delta is actually detected at 3 sigma. And the value of delta that you find is this, which is more or less the cosmic horizon. What is interesting is that in this case you detect a distance, and this distance can be pushed back to the beginning of inflation, undoing the expansion of the universe. The value that you find is not insensible, it's 4 times 10 to the 12 GeV times a correction factor, which is 1 when the number of e-folds is 60. Now, let me show you what happens next. This is the first story. The next thing you can ask is what happens to the tensor to scalar ratio. And we found in all these examples that we saw numerically first, that the tensor to scalar ratio tends to increase by about an order of magnitude around the scalar delta, the scale delta. There is even a little analytic argument tailored on the case of exponential potentials, which shows you that this should be the case. The next question you can ask, and this is ongoing work that I'm presenting here, is that you can compute the non-Gaussian contribution of these terms. Now, you can do it, of course, with approximations, some of which are standard in the story, and like, for instance, ignoring the initial singularity, pushing it back. And this I'm forced to do because we have no control about on the higher derivative terms. But if you push it back, what happens is that you have 2 types of phenomena. The epsilon parameter jumps almost vertically in these models. There's a 0 and then it approaches the small value that corresponds to the inflationary phase. If you compute, taking these 2 ingredients into account, the contribution to the 3-point function, and you play with the fact that I told you that you have to be careful about the initial singularity, the value k over delta of order 1 corresponds, if you use that determination we told you about, to L of order 10. So it means that if you take cosmic variance into account, you shouldn't go beyond 0.5, which is L about 5. Below that is completely unreliable. And at the same time, for L equal 30 or so, everything should converge. The 1 here is Malpasini's result. And now what you see is that you have 2 types of situations. If you have merely a jump of epsilon, and this, of course, will apply also to scenarios which don't have to do with the climate scalar, but to any situation in which the scalar at some point slows down as it should to attain zero, Then you have an amplification factor in this region with respect to Maldacena as a result of about 2. What is interesting is that if you take also the climbing phenomenon into account, you have an extra source of amplification which comes from this region. And now the amplification depends strongly on the number of defaults. If the number of defaults goes up to 66, not much happens. It's similar to this one. If it goes beyond 66, then there is this exponential that I showed you before, and the increase is sizable. And so this has to do with the equilateral case, but the squeezed case has a similar behavior. The other phenomenon, which is peculiar of this climbing story, is that there is a logarithmic instability of isotropy. In cosmology, what you can consider is let the system evolve and perturb it. If the perturbation grows, then the system is unstable. The perturbations with k not 0 are stable. The k equals 0 perturbation is logarithmically unstable. So if you take this story at face value, it would indicate an instability of isotropy, which is interesting because since these models start from higher dimensions, then in the spirit of this multitude of string options, they could go to 4 dimensions by a mechanism that we would not control, but would be indicated by the instability. Now I would like to attack the second part of this discussion. If you don't break supersymmetry, you know there is a huge zoology of string vacuum based on Campagna, manifolds, orbifolds, or the like. The problem with this vacuum is that, as we have, there are many. They depend on continuous parameters, which are called moduli, and this makes any kind of prediction very complicated, to say the least. Now, what happens if you try to compactify the theory in the presence of broken supersymmetry? And the simplest case to examine is when these tactile potentials are present. What happens is that typical vacua, like ADS vacua, which you can build, are unstable. You get violations of the Brighton-Loner-Friedman bounds, for those who know what it is. Essentially, instabilities like tactile instabilities in flat space due to mixing the internal modes. But there is one notable exception. This notable exception is the counterpart of Kaluza-Klein circle compactification in the presence of the tactile potential, what they call 2000 vacuum. They discovered them in 2000, and the crucial difference is that the internal circle is replaced by an interval. And this is the solution. The key property of the solution is that it has weak coupling at one end and strong coupling at the other. Yet, if you look at the behavior near the strong coupling region, which is determined by the tactile potential, you find that the behavior is as though the tactile potential were not there. It approaches the behavior strong, but strong couple, but universal, like as though the tactile potential were absent. And the reason why it's interesting, because remember that one of the models I told you about, which has this potential, has spontaneously broken supersymmetry. So it could be that there is a link between this very peculiar unexpected behavior there. But let's come to the key point. How you study the stability of this system? This is the most complicated part of the story. It's the scalar perturbations. You do what you perturb Einstein equations, and you find a perturbation equation for the scalar mode. You find also a perturbation equation for tensor mode, but it's much simpler and it's stable. In this case, it looks very complicated. However, it is possible to reformulate it in a way which is along the lines of what people call the supersymmetric quantum mechanics. So the operator can be factored in terms of first order ones up to a positive shift. And this relation indicates that the system is stable. However, to be more precise, since it's an interval, you should look at boundary conditions. And if you do look at boundary conditions, you find something even more surprising. First of all, the potential for the Schrödinger form for perturbations is singular at the two ends of the interval. And it's essentially on top of an integrable potential. See, this potential is an integrable potential, solvable in terms of the Legendre function, and the actual potential is on top of it. What you find is that all boundary conditions are unstable and assigned to a single one. And the single one corresponds to a massless graviton. So you find a massless graviton in this compactification, a massive scalar, so the Kaluza-Klein scalar becomes massive, it's not a modulus anymore, so much so, exactly like what's happening with the internal size, which was fixed by tension. And then there are other modes. In other words, I mean, there are boundary conditions that even if you look at things closely and precisely, make the system stable. Very quickly on a couple of recent developments. If you want to describe one of these theories, saying that the string theory is a theory of strings is very naive. We know that there are lots of extended objects, lots of solidon-like objects, branes. And if you ignore the tactile potential, you can classify, by conformal theory techniques, the branes present in these models. This we did long ago. The question, what does the tactile do to this brane configuration? I'll try to be quick. This is just to show you something which is very much along the lines of the formulas that I flashed at the beginning. There's a very well-defined conformal theory technique for constructing these branes, however, ignoring the tactile potential. What happens if you do that? Then you find the standard classification of BPS branes, and also you find some uncharged branes. These are the so-called supersymmetric BPS branes, and these are the uncharged branes, which break supersymmetry. Now, what happens in these models if you take the tactile potential into account? Apparently, you find something discouraging, because you seem to find solutions which close up in very limited intervals of order square root of alpha prime. So the system seems to be not responding in the right way. However, this is not the correct interpretation, because the one-dimensional case of this type, where space-time is limited to a finite distance in an internal direction, is the two-dimensional vacuum. So this solution that you find, and it is complicated because the set of equations becomes involved in this case. However, whenever one of the three ingredients, tension, curvature, and flux, dominates over the other, the system becomes integrable. So in limiting cases, you have lots of conservation laws, if you want. And by this, you can conclude that these solutions, which apparently look unstable, are nothing but lower dimensional generalizations obtained numerically of the Dudas-Murat vacuum, possibly containing a brane theory. So in other words, if the Dudas-Murat vacuum is the T1 S1 compactification, these are Tn compactifications, counterparts of that. So it's not just one example, there's a family of solutions. Of course, it's more complicated to deal with that. What is most interesting is the following. Suppose you start from the Dudas-Murat vacuum, which I said is like T1 compactification, S1 if you prefer. And you end up in one less dimension with a flat space. And now study the branes in that space, which is a vacuum. What happens is that the uncharged branes are exact solutions in this compactification, and the charged ones, which are more complicated, we couldn't solve them exactly, but asymptotically they have the right charge and tension behavior. So in other words, this vacuum behaves well, it's stable, it has the proper branes, and the branes behave as they should. Summarizing. The cosmology part, I try to tell you that these models sort of bring you naturally to this modification of the almost scaling invariant spectrum for cosmology with an extra parameter, that this parameter can be somehow extracted from the data better at higher latitudes. The result is not unreasonable. And the behavior of epsilon and the fact that typically the model approaches an exponential behavior very early, when epsilon is still large, allow some approximations that make it possible to compute analytically the non-Gaussian contribution. The second part of the story I told you has to do with compactifications, and the first statement is that we have analogs of the circle compactifications and Tn compactifications. The circle ones have been detailedly proven to be perturbatively stable. The others not yet, but I mean, they should be, because they're more indirect, they are defined numerically. And in the Dudas-Morat vacuum, which is this 9-dimensional setup which ends up in flat space, the branes have the conventional behavior, and charged branes are even exact solutions of that vacuum. And charged ones can be known, I mean, can be determined in the leading behavior at large distances. Thank you very much.
Thanks, Augusto. Are there comments or questions?
So with the setup, what would be the mechanism for a standard model like a MATLAB? What would be the kind of appropriate method for obtaining matter here? Branes?
Same thing. Bulk or branes, but the difference is that the moduli are typically stabilized. And the real question is whether the small oscillations have negative mass squared. Notice that I could talk about tachyons, because in these cases, one ends up in flat space, so there's no issue of Lagrangian free band modification. So you have, these are glimpses of what it could be, of course, these are very simple examples, preliminary moves, but yet the moduli are stabilized, and the system is stable, and then you have this intriguing fact that in cosmology, when you have this flat, say, inflation-like cosmology, they sit precisely at the point where you are forced to be with coupling.
Other further comments? Yes.
I have a question on how this connects with the other evolutionary scenarios, in particular in many sectors of string theory, the lower energy effective field theory would look like a double field theory, right? And where
Let me make a preliminary comment. The model only contains one coupling from the top-down perspective, the potential that forces you to climb. The remainder, the potential that brings you to an inflationary phase, it's something that you have basically, I showed you the Stravinsky case, but whatever potential you put can be added to this steep one. So we have no prediction on that. Only the top-down part. Secondly, in this case, you are working with reactivables. So it's not type 2b, it's a truncated type 2b, and therefore the duality is reduced with respect to the type 2b. So it's not double field theory as such. It is a truncation of that as pertains to the truncation of the type 2b you start from. So the only double that you have to bring home is the fact that you have something that forces you to climb and confines the dynamics to decoupling.
So should I see it as an approximation to the full field, or as a different sector?
I would say it's a different sector, because the reactival is different from type 2b. No, it's a different theory. It's a different sector. Now, of course, everything is in principle related by orbital for the reactive projection, but the spectrum changes in a non-trivial way, so it's not exactly the same story.
Okay, I don't see any further questions, so let's thank Augusto and all the speakers for the first section.